Welcome everyone. It's my pleasure to introduce Kirill Krasnov for our 27th IFS seminar. Kirill is a professor in Nottingham, and I had the pleasure to interact with him when I worked in Potsdam and he was visiting.
Okay, thank you for the invitation. So, the subject of my talk is I'm talking about formalism for 4D general relativity, which is unusual in the sense that one codes the geometry in what I call here triple of two forms. So, the main message of the talk is that there is this very powerful formalism, powerful both geometrically and computationally. It's a formalism for GGR. As I said, it codes the main kind of the main variable, the main dynamical object in this description of gravity is a triple of two forms, satisfying some simple algebraic relation. I'll explain all this. This formalism is far from being new. It was discovered almost 50 years ago now. Also, many aspects of this formalism are very well known and standard in the math literature on 4D geometry, differential geometry. So what I want to do in this talk is to explain you geometry behind this formalism and also try to explain in what sense, at least in my view, this is superior to the usual metric one. At the very basic level, what I'm talking about is a convenient and useful choice of variables for GR, just described in general relativity. And it's about choice of variables. So let me start with very basic motivations. So as we all know, and as was the main discovery or the main insight of Einstein, that gravity is geometry. Einstein was led from this insight to his dynamical theory of GR. GR is the dynamical theory of the spacetime metric. Here we have Einstein equations. We now understand that vacuum Einstein equations, it's easier to talk about vacuum, to start with vacuum, and then kind of, if we need to, we can add the right-hand side, how matter affects geometry. But at least if we talk about vacuum Einstein equations, then we now understand that these are the unique diffeomorphism invariant second-order in derivatives equations that can be written down for the metric. There is just nothing else you can have. In 4D, this is particularly pronounced. In higher dimensions, this is also true, but one needs a further assumption of quasi-linearity, linearity in second derivatives. But in 4D, it's just the only thing that we can write, and then the full system of Einstein equations, once you have vacuum, you couple this with the insight that matter must affect geometry in some way, and, well, it's basically, again, this is the only thing you can write, provided stress. We want something with the symmetries of Ricci tensor to affect the geometry. So stress energy tensor is natural, and also stress energy tensor is conserved, and then Einstein tensor. Oops, I'm missing G mu here. It's a typo, but Einstein tensor is conserved as well. The divergence is equal to 0 both sides, and so these equations make sense. As we all know, predictions of GR agree very well with all observations about the universe. Cosmology, kind of in the last 30 years maybe, and more recently gravitational waves. Now that we started seeing black holes through the eyes of the gravitational waves observatories, again, GR predictions are very well agreeing with observations. Nevertheless, GR is a very difficult theory to deal with. Mathematically, Einstein equations are complicated, non-linear, hyperbolic, mode gauge, second-order PDEs for the metric. Even the statement of the fact that they're well posed was only proven many, many years ago, or many years after Einstein formulated his equations. So in 1952, Jacques-Brouillard has proven it, and more recently in the era of gravitational waves, in the era when we need to understand how two black holes collide, this non-linearity and the difficult character of GR is a pain. So in particular, it's a pain if we want to put GR on the computer and do numerical relativity. It's been many years of efforts of the community to even be able to simulate GR on the computer. So it's a difficult theory. At the same time, there are hints of hidden simplicity in it. There are many parallels between Jan Mills' and GR. Some of them I'll mention here. At the same time, Yang-Mills or electricity and magnetism are much simpler than general relativity. Now, so what are the parallels? One very kind of stunning statement comes by studying GR on shell or studying scattering amplitudes, graviton scattering amplitudes, as predicted by general relativity. And then one learns that in a certain sense, certain precise sense, GR is a square of Yang-Mills. In other words, one can recycle Yang-Mills scattering amplitudes, put them together in some clever way, and obtain GR scattering amplitudes. In particular, this is completely manifest in the cubic interaction, kind of two gluons, one gluon. This is not a very physical process because in Minkowski signature, actually, this amplitude is 0, but there is a vertex like this in the Lagrangian of both theories, and if you evaluate it on shell, you see explicitly that GR cubic vertex is a square of Yang-Mills. So that's very impressive, and so this suggests that there could be, and now we know that there is a relation between these two theories. Also, both of these theories have the so-called self-dual sector, which is integrable. And, well, then we have Penrose's twistor program that established the integrability and also beautifully linked all this integrable stuff to complex analysis and algebraic geometry. All these statements are invisible in the usual metric formulation. This motivates looking for some reformulations or simplifications, and one formalism that is a major step towards geometrizing GR is the Cartan's frame formalism. It's a very deep kind of set of ideas. It goes much further than just description of Riemannian geometry, because it's applicable to describe geometry of the so-called G structures. So let me sketch the ideas here. Probably you know the frame formalism, at least to some extent, but I still want to sketch some of the ideas here because I will use this. It will be a step for me to go to this formalism in terms of two forms. So the idea of Cartan's geometry is that given some geometric structure, which is a collection of tensors, for example, metric tensor, one consider all possible frames, and frame is a basis in the tangent space. So you consider all possible frames compatible with the structure. So, for example, in the metric case, this would be all orthonormal frames, or maybe orthonormal-oriented frames. And in many cases, what arises, depending on your collection of tensors, what arises is a principal G bundle of such compatible frames, where G changes, and one calls this type of geometry of G structures. But in the Riemannian case, one obtains the principal bundle of orthonormal frames is either SO or SO and -1 principal bundle. And this leads to powerful formalism. So kind of the geometry of this formalism is one starts with the principal bundle. This is a bundle over space-time manifold where the fiber is the group. Then concretely one views a frame as a map from Rn to the tangent space of the manifold. And then all orthonormal frames are mapped one to another by the action of the group. And given such a map, one builds a soldering form. Soldering form arises first as a map from the tangent space to the principal bundle to Rn, or it's basically Rn valued one form on the principal bundle. And then, well, this is the way you construct it. If you have a vector field tangent to your principal bundle, you first project it to the manifold. This is pi of x, and then you get a vector field in the tangent space to the manifold, and then you take θ minus 1, kind of inverse this frame map. Take θ minus 1, you obtain something Rn valued. So that's the construction of the soldering form. And then it starts its life as this one form in the principal bundle, but actually it descends or it defines a one form, Rn valued one form in the associated Rn bundle. And so at the end of the day, very concretely, one works with Rn valued one form. One can do that even on space-time. So the most concrete formalism is you just take n one forms on your manifold. There are 2 points of view on this. Either you start with a metric and then you consider collections of one forms that are orthonormal or with respect to the metric, But actually, most usefully, a kind of dual or opposite viewpoint is possible. You can just start with a collection of one forms and declare them to be orthonormal. And this defines the metric. So this is probably the most useful viewpoint in the sense that one encodes the metric into a collection of one forms. And then the next basic step of this formalism is one takes metric covariant derivative. So if there was a metric to start with, and this is an orthonormal frame, of course there is metric covariant derivative. If there was no metric, and you use this one forms to define the metric, you define the metric defines the Levi-Civita covariant derivative. And then it's very easy to see that if you take Levi-Civita covariant derivative of these frames in direction of some vector field, because Levi-Civita preserves the metric, and this was an orthonormal frame, well, these guys should be expressible in terms of orthonormal frame as well. So there exists a collection of coefficients, such the covariant derivative of ease of these one forms in the direction of any vector field is just a bunch of coefficients, is a linear combination of the one forms. This is powerful equation because some immediate consequences of it, you define the dual objects to this, you multiply both sides of this equation by the dual objects, and then you quickly see, there is simple algebra, that these connection coefficients with one index raised with the metric that one has in Rn is necessarily antisymmetric. So these omegas are really components of SON or SO1 n minus 1 connection. This is one consequence of this equation. Another consequence is you take another covariant derivative on the left-hand side, you antisymmetrize. So this is Ricci tensor of the Levi-Civita, but on the other hand, you apply this covariant derivative to the right-hand side of this equation. You get term like covariant derivative omega, and then another covariant derivative of E, but covariant derivative of E is omega. So you get covariant derivative omega, omega, omega term, and then antisymmetrization. So you see from this formula immediately that the curvature of this connection omega encodes Riemann curvature. You get access to Riemann curvature by computing the curvature of this connection omega. And this is where the power of this formalism comes from, but there is more to say on this. Another kind of miracle and beauty of this formalism is that the equations on the previous slide, they descend to equations written with differential forms. So to see this, let me take this equation that I had on the previous slide, covariant derivative of E. There is no symmetrization or anti-symmetrization on these indices here. And then we project on the space of two forms. So we anti-symmetrize mu nu. Because Levi-Civita connection is torsion-free, this anti-symmetrization here descends to the exterior derivative of the one forms, EI. On the right-hand side, we just have the wedge product of these forms. So we can of course compute this projection, but then the beauty of it, and as I said, a miracle, is that the projection of this equation carries exactly the same number of equations as the number of unknowns, because this is two-form R4 valued. This is basically R4 valued two-form. There is another type of this, must be I. So in particular in 4 dimension, but it's true in any dimension. In any dimension, the number of these connection coefficients is the same as the number of equations here. So this tells you that these equations completely characterize these connection coefficients. Then the curvature of this connection is also computable only using the operations of exterior derivative and wedge product. And so we get a very powerful statement that to compute Riemann curvature, well, we just encode metric into this collection of one forms. Then we take exterior derivatives, write these equations. They are linear equations for the connections. We solve them. Again, we take exterior derivative wedge products. We compute R. And basically, this is Riemann curvature. So one never has to do anything else, just take exterior derivatives, wedge products, and solve linear equations here. In particular, one never needs the metric or Levi-Civita connection in this formalism. Also, Einstein equations can be stated, vacuum Einstein equations can be stated in the same language. So here is a statement of, this is R mu nu is equal to lambda G mu nu in the language of differential forms. So this is all beautiful. Another simple point is that there is an action principle that realizes these ideas. in this action principle, it's a functional of the soldering forms E, connection coefficients, and that's the action. So no metric appears explicitly. Another basic point is that this formalism of soldering form is not optional if one wants to couple gravity to spinors. Okay, but so this is a beautiful formalism, but so why is it not the end of the story? Why don't we use this and be happy with it? And this formalism is still rather difficult to deal with in explicit calculations with GR. So first of all, there is more components in this tetrad or frame in 4 dimensions. This is R4 valued 1 form, so there are 16 components in E. We've enlarged the number of components in E. This, one can say, is less economic than in GR, because GR is just metric with its 10 components. But something else happens as well. This is a first order formalism with only first derivatives in the action. The kinetic term is schematically of the form E d omega. Of course, there is also omega omega component coming from here. So basically, if you expand around, let's say, flat background, your quadratic order of the expansion is E d omega plus omega squared. And then there are 16 components in the soldering form, 24 components in the connection. And this is clearly mismatch, 16, 24. So for example, this term here, just E d omega, this quadratic form is not invertible, even after one fixes the gauge. If one has omega squared here, the quadratic form after fixing the gauge becomes invertible, but then one gets kind of very complicated or reasonably complicated propagators here. In particular, well, one gets kind of the usual EE propagator, metric, but clearly one also has metric connection propagator, and one gets connection propagator, which is not simple. And so there is some kind of a mess here if one starts doing perturbation theory. The propagator in this theory is complicated. This is similar situation in the metric first order formalism, where one can take Christoffel symbol to be an independent object, and then expanding the Einstein-Hilbert Lagrangian, or rather Palatini Lagrangian, one gets schematically H d gamma plus gamma gamma. There is even bigger mismatch here, and the propagator here is also quite complicated. In particular, the gamma gamma propagator is rather nasty. For me, it is this consideration that suggests to look for something better. And also, of course, I mentioned self-dual sector. So all this, there is no link to self-dual sector with its simplicity. Not yet. So this leads me to consider self-duality in 4 dimensions. So the formalism that I'm talking about is based on self-duality and some exceptional isomorphism, one can say, that happens in 4D. The basic fact is that orthogonal group, Euclidean orthogonal group, of course, here, this is SO4, is not simple. It's a product of 2 groups, mod Z2. There is analogous statement for the Lorentz group. So, Lorentz group is really SL to C. A related fact is that the space of 2 forms in 4D splits. Lambda 2 splits into self-dual, anti-self-dual 2 forms. In particular, this means that the spin connection splits into 2 halves, where both halves, chiral halves of the spin connection are SO3 connections. And it is this observation that leads to the chiral formalism for GR. The chiral formalism keeps only 1/2 of the spin connection. Now I would like to describe the geometry of 2 forms in 4D. So the idea of the formalism that we're going to build is that we want to encode metric into 2 forms. In the frame formalism, we encoded the metric into a collection of 1 forms, which were declared to be orthonormal. Here we'll take instead 3 2 forms, and we'll declare them to be self-dual, and this will encode the metric. So let's see how that can be possible. Given a Riemannian manifold, we have the Hodge star. It defines decomposition lambda 2 into lambda plus lambda minus. It's not difficult to check that if my metric is a Riemannian signature, so say Euclidean, and I think here I'll be explaining mostly the Euclidean signature case. So this is why I now stick to Riemannian geometry. This formalism is also possible in the Lorentzian case, but some things need to be modified. At least some groups, the groups that will appear will be different, but so let's stick to the Euclidean case. So in the Euclidean case, the decomposition into lambda plus, lambda minus is such that the so-called wedge product metric on lambda 2, this is the metric that arises if one takes an arbitrary orientation, arbitrary volume form, and you take two forms, you wedge them together, you define by the volume form. This gives you symmetric pairing in the space of two forms, which I'll refer to as the product metric. And then in the Riemannian case, this product metric restricted to lambda plus is definite. In fact, this is the way to differentiate between different cases. In the other possible case, there is also a split signature, right, in 4 dimensions. So there are just two cases when lambda plus and lambda minus are real subspaces. In Lorentzian signature, Hodge star, its eigenvalues are plus minus square root of minus 1. So lambda plus and lambda minus are necessarily complex spaces. But if they're real, then there are just two possibilities. Either the restriction on lambda plus is definite or it's indefinite. When it's definite, you're talking about Riemannian metrics. When it's indefinite, you're talking about split signature metrics. In the Lorentzian case, a bit more to say. Space lambda minus is the complex conjugate of space lambda plus, and that captures the Lorentzian geometry case. But if we have the Hodge star, we have the split, but it's also known that the knowledge of Hodge star is equivalent to the knowledge of the conformal metric. And so we can encode the Hodge star into the choice of a rank 3 subbundle lambda plus of lambda 2. And of course, we want to demand that the restriction of the wedge product metric to this subbundle is definite. So we get kind of isomorphism choosing lambda plus 3-dimensional subspace of lambda 2 such that lambda plus is definite is the same as choosing conformal metric, which is Riemannian signature. This statement is nicely captured by this group coset isomorphism. So the choice of lambda plus in lambda 2 is the choice of 3-dimensional plane in the space of signature 3, 3, because this wedge product metric is in lambda 2 has signature 3, 3, and choice of a definite subspace is this group coset. But SO33 is the same as SL4. This is basically the same as SO4, and then so it's clear that the choice of a 3-dimensional hyperplane in the 6-dimensional space is the same as a point in this coset, but this coset just describes our Euclidean metrics, or Euclidean conformal metrics. It would be all metrics if we take GL4 instead. One can also describe the arising metric explicitly. So if one has a triple of two forms, there is a simple formula that cooks up the metric. You insert vector field into one or two forms, another vector field into the other, wedge with the third one. This is a top form. You divide by some chosen volume form, and you get a metric. And beautifully, this formula captures the idea that I said is the key geometric idea here. One takes a triple of two forms and declares them to be self-dual. And one can check that it is this metric that makes B1, B2, B3 self-dual. However, this does not yet lead to useful formalism. Useful formalism arises. One needs a bit more. Useful formalism is, it should mimic in some way the frame formalism. So now I want to set up analog of this frame formalism. I want now to consider orthonormal frames for lambda plus. Any such frame can be viewed as a map from R3 to lambda plus. The new feature, which was not available, did not arise in the usual one frames formalism, in Cartan's formalism, is that here naturally we have a metric on both spaces. Well, we have the standard Euclidean metric on R3, but also on lambda plus we have the wedge product metric. It is very natural to require that these two metrics coincide. Not just natural, but necessary. Basically, because if one wants to interpret these two frames orthonormal frames for lambda plus, then this is a necessary requirement. And so in the basis, one ends up working with two forms, triple of two forms, which satisfy the condition that sigma I, sigma j, where indices ij takes value 1, 2, 3, is proportional to delta ij, metric in R3. Well, then one more or less mimics what happens in the usual frame formalism. One starts with some principal SO3 bundle, then passes to associated bundle, but at the end of the day, one just works with two forms, triple of two forms on the spacetime manifold. But importantly, these two forms satisfy this algebraic condition here. How do these two forms encode the metric? This is a simple count. If you are to specify triple of two forms in 4 dimensions, this is 18 functions, because a single two form is 6 functions. So one has 18 functions to specify, and here there are 5 algebraic conditions. So 18 minus 5 is 13, and this is 10 plus 3, 10 metric components, and 3 orientation of the frame. These are just these SO3 rotations, which are still arbitrary. And then one proceeds with some calculations analogous to what was happening in the frame formalism, but here one needs to work a little more. The main difference now is that so the idea of this formalism is that you want to declare this triple of two forms the main objects. And one wants to say that metric is not really available, or you would, of course, metric is defined by sigma i's, but one would like to avoid explicit references to this metric and have a formalism which works just with sigmas. And so it takes some work to establish such a formalism. Kind of the main, well, everything is dictated. Possible geometric objects in this story are dictated by representation theory of SO4. SO4 still acts on all these objects. It acts, well, like one can say that the usual frame in Cartan's formalism, Lorentz groups still act on the frames. The way this is happening is that Lorentz group acts in the tangent space to the manifold, as well as it acts on the frame itself. If one remembers what the frame was, if I go back some slides, so one viewed the frame as a map like this, and if Lorentz group acts on the tangent space as well as on the Rn, then frame is an equivariant map. So the same happens with these two forms. Lorentz group acts on the tangent space to the manifold. This induces some action on two forms, and half of Lorentz group, namely SO3, acts also on R3. And this sigma is an equivariant map. Then, so to set up the formalism which links to usual Riemannian geometry, one starts by using Levi-Civita connection, but at the end of the day we'll get rid of it. So it was the same trick as was happening with the frames. We started with Levi-Civita connection. Here I considered covariant derivative of the frame and then established some equation, and then eventually things were projected to the level of differential forms. So the same happens with formalism of two forms. So one starts with two forms. One can say that metric is defined by these two forms, and then an index of these two forms can be, one of the indices can be raised, and this leads to a triple of endomorphisms of the tangent bundle satisfying the algebra of imaginary quaternions. One can show that if metric is defined by sigmas, then raising index of sigma with this metric, the objects one obtains satisfy this algebra of imaginary quaternions. And one uses these objects to decompose all tensors into irreducible subspaces. So at this level it becomes technical. I'm not sure I want to explain you this story. So maybe let me concentrate instead on the main point. So there is some decompositions which are just established by representation theory, and as I said, the main objects are these two forms with one index raised. But the main point is that if one takes a covariant derivative of two forms, then a certain identity is true. Well, that's the main equation. Covariant derivative of two forms can be expressed in terms of some connection coefficients times two forms. It takes some work to establish this equation, but this is possible. And so this equation is the existence of some connection coefficients. This is analogous to what we had in the usual frame story, where covariant derivative of one forms was a linear combination of one forms. And the key point is the same as in the frame story. This equation can be projected to the space of three forms. If one does this projection, then this covariant derivative becomes exterior derivative. And so then we have the proposition that the connection coefficients are completely determined by the projection of these equations to the space of three forms. At the level of this projection, the equation is stated in terms of exterior derivative and wedge product, exactly as in the frame formalism. And solving these linear equations for the A coefficients, one obtains explicitly, well, the explicit answer for them is that they are determined by the Hodge dual of the exterior derivative of sigmas. Well, here Hodge dual, of course, is the metric Hodge dual, but it's also possible to take a viewpoint that metric is never introduced. So the basic objects are sigma, and then you write these equations in terms of exterior derivative, and this defines the connection coefficients, because this is a system of linear equations for the connection. So from this point of view, metric is not needed. Then one does the same trick as in the usual frame formalism. One takes another covariant derivative. On one hand, this gives access to Riemann curvature or some subset of Riemann curvature. On the other hand, this is just the curvature of the SO3 connection A. Then analyzing representation theory a little more, one sees that what is recovered here, or the part of the Riemann curvature that one gets access to via this equation, is just half of the Riemann curvature. One can say that this is the half of the Riemann curvature, which is self-dual with respect to a pair of the indices. And then we have a well-known fact of 4D Riemannian geometry that one can encode Einstein condition into the statement that the part of Riemann curvature which is self-dual with respect to one pair of indices and anti-self-dual with respect to the other is zero. And this becomes a very simple statement in the language of two forms that the curvature of this SO3 connection is arbitrary linear combination of self-dual two forms. This is precisely the statement that there are no anti-self-dual two forms appearing in this decomposition. F proportional to sigma becomes a statement of Einstein equations in the language of two forms. Summarizing this story, one encodes metric into a triple of two forms, satisfying these algebraic conditions. Then the basic equation of the formalism is certain three-form equation. Exterior derivative of sigmas is expressible in terms of certain connection coefficients. And then Einstein equations is a statement that curvature of this SO3 connection is expandable just in terms of sigmas. There are no anti-self-dual two forms appearing here. If one wants to state full Einstein equations with the right-hand side metric or arbitrary stress energy tensor, then it turns out that what you add here is precisely anti-self-dual part. So there is a certain combination. You can take stress energy tensor, raise its index with the metric, contract into sigmas, and there is a natural term that can be added here, which encodes stress energy tensor. At this level, as in Einstein-Cartan theory, all equations are stated in terms of only exterior derivative and wedge products. So again, I'm comparing here with the usual frame formalism. So far we have a formalism. I hope I convinced you that it is capable of describing Einstein equations. But what is not clear at all at this stage is why this is any superior to the usual frame formalism. What makes this better? It looks like it's completely parallel, but one needs to work harder. This is more esoteric because two forms instead of one forms. So why is this any better? The difference between them is the types of operators that appear in the linearized theory and also as a result it produces much more powerful perturbation theory. Also, this formalism is directly adapted to describe instantons because self-duality was key here. So let me first sketch the self-duality story. Let me start with Yang-Mills self-duality equations. So Yang-Mills self-duality equation is a statement that one of the two chiral halves of the Yang-Mills field strength is zero. Beautifully, if you linearize this condition, you get very nice complex of differential operators. So you get gauge transformation sitting here, then exterior covariant derivative with respect to connection maps you to Lie algebra valid 1 forms. This is connections. And then exterior derivative on connections projected to the space of self-dual 2 forms maps you to lambda 2 plus. Beautifully, this complex is elliptic. Well, the composition of these two is zero, and moreover, image of the first map is the kernel of the second map, and this is important. This complex plays the key role in understanding local properties of the instanton moduli space, and also beautifully, out of elliptic complex like this, one can fold it. One can take this lambda 1, put it on one side, and then consider the operator, which is this operator plus the adjoint of this one. And the arising elliptic operator here is super beautiful. It's just a Dirac operator. It turns out that this is a certain version of the Dirac operator. All these properties, all this story has analog for the case of gravity, but this is what needs introduction of 2 forms. So let me start with gravitational instantons. I'll define gravitational instantons as Riemannian metrics for which one of the 2 halves of the Riemann curvature vanishes. This definition is probably different from the standard. There is another standard definition in the literature, which is gravitational instantons are Riemannian metrics with half Weyl curvature vanishing. Here I'm requiring more. I'm requiring half of the Riemann curvature vanishing. So requiring this gives automatically metrics which are Einstein and Ricci flat, because Einstein condition is self-dual as well as anti-self-dual zero. Well, anti-self-dual of the self-dual is equal to 0, but all of the self-dual is 0, so this in particular is implied. And the scalar curvature is a component of Riemann plus plus, so if this vanishes, this is Ricci flat as well. The 2-frame formalism, and these 2 forms, is ideally suited for description of gravitational instantons, because remember, as I explained, the curvature of my SO3 connection encodes precisely Riemann plus. So if curvature vanishes, then there exists a gauge in which the connection is 0. So we are led to very simple description of gravitational instantons. Gravitational instantons are triples of 2 forms, satisfying the algebraic condition sigma I, sigma j proportional to delta j, which are closed. Because in this case, remember that exterior derivative of sigma determines the connection, and so if they are closed, connection is 0, curvature is 0, and we get gravitational instanton. So in particular, in the language of 2 forms, these instanton conditions clearly take first order form. They're first order in derivatives. This is completely analogous to what happens in the Yang-Mills case. Yang-Mills instanton, or Yang-Mills self-duality equations are first order conditions on the connection. In the case of gravity, using description in terms of 2 forms, gravitational instanton condition is also first order in derivatives. And, well, this description of gravitational instantons is well known. So, for example, Iguchi-Hansen metric, if one looks at their paper, it was obtained exactly by calculating, making metric ansatz, calculating this connection, and then requiring this connection to be 0. There is also relation to hyperkähler manifolds, which probably I should skip for now. But basically, these gravitational instantons, what I call gravitational instantons, are just hyperkähler manifolds in 4 dimensions. Okay, let me skip it for a second for now. There is a beautiful action principle for gravitational instantons that realizes these ideas, and beautifully this action principle arises just by dropping a term in Plebanski action. So Plebanski action is this action where there are three independent fields to vary with: sigma, A, psi. One gets three equations listed here on the left. So the point is that one can just take Plebanski action and drop the AA term in the F and consider just the action which is sigma I dA minus psi sigma sigma. So I'm also dropping here the cosmological constant term. Now the statement is that critical points of this action are precisely gravitational instantons. This is because, well, this condition or this term is there just to guarantee that algebraic condition on sigma is satisfied. And then if I vary with respect to A, I get the statement that sigmas are closed. So this is exactly my instanton conditions. So it's a very simple action. It's useful. One can work with it, even do perturbation theory. But even more useful action arises by further trick. One says that because sigmas are necessarily closed, therefore you can write them as some kind of background sigmas which encode background and which can be topologically non-trivial, plus exterior derivative of some one forms. And then you substitute this into the action. This term drops out because by construction this is automatically closed, and one gets an action psi sigma 0 plus dA, sigma 0 plus dA. This action is even more useful. There is a very simple, nice perturbation theory arising from here. One can compute with it. So for example, one of the applications is one can compute the so-called Behrens-Gilly currents of self-dual gravity, starting with this action. And this is not a difficult calculation. So this formalism is actually useful. In particular, I talked about propagators. In all the previous formalisms, propagator was not easy, but here the propagator is super nice as well. I'll sketch it when I talk about Plebanski complex. So this is my next slide. The statement here is that linearization of the gravitational instanton equations gives rise to a simple, beautiful complex, elliptic complex of differential operators. So the complex is, you start with vector fields, there is an operator that maps you to two forms, or rather perturbations of two forms. And then another operator maps you to connections. And finally, there is last operator that maps you to basically a copy of R3. So these operators are explicitly described here. Details are not very important. Dimensions are 4 to 13 to 12 to 3. And dimensions, the alternating sum of dimensions is 0, as it should be for an elliptic complex. And then beautifully, there is a gauge fixing of this complex, which after you do it, you fold it, get an elliptic operator. And the arising elliptic operator is sum of two Dirac operators as well, similar to the Yang-Mills instanton case. The difference with the Yang-Mills case is that the complex was simpler. Complex had just 3 spaces. This is 4-term complex. And also the elliptic operator that arises is a sum of 2 Dirac operators rather than just a single one. And so here I will not talk about scattering amplitudes, but one can compute with these formalisms and one can actually write some. In a recent paper of mine, with a student of mine, we calculated using GR perturbation theory, which is based on this Plebanski formalism, using method of Behrens-Gilly currents, we calculated MHV graviton scattering amplitudes. We've done calculation completely analogous to how Yang-Mills MHV scattering amplitudes were calculated many, many years ago. And our calculation is completely parallel, of course, a bit more involved because gravity is more complicated than Yang-Mills, but at the level of philosophy, logic, it's exactly the same calculation. So this formalism is useful and can be used for actual calculations with GR. So let me summarize. I describe a very powerful formalism. I mainly talked about 4D Riemannian geometry case, but as I said, it also works with Lorentzian case. Lorentzian case is a bit more complicated because these two forms must become complex valued, and then one needs to impose reality condition on them. Reality conditions just as the two forms are wedge orthogonal to their complex conjugates. Anyway, so there is a formalism for 4D geometry, metric geometry, which works in terms of triples of two forms. This triple of two form formalism is completely analogous to Cartan's one frame formalism with some differences, but the analogy is rather perfect. Kind of at the level of equations, there is precise analogy. The field equations in this formalism, as in Cartan formalism, are in terms of the exterior derivative operator. So to compute here, one never needs to compute the metric, as in Cartan formalism. And once again, to summarize, what is powerful about this formalism is that many facts about geometry in 4D are obtainable in this formalism in a simpler way. I could give many examples of this. I didn't have time to talk about. There is a lot to say on this point, but in particular, we've seen how linearization of field equations in this formalism gives rise to nice elliptic complex. So it is in this sense that perturbation theory based on this formalism is simpler than in any other formalism. I'll just finish with a comment that this formalism is the next step for this formalism is a problem that is too difficult in normal metric GR, and there are some possible problems here are listed. But this is, in my opinion, and my experience with this formalism tells me that it's incredibly powerful, and probably it has applications apart from those that I described and apart from those that are understood already. There's probably more than this formalism can do. And I'll end on this. Thank you very much.
Thank you, Kirill. Do you have time for questions?
Yeah. I have
Okay.
some time, yes.
You mentioned numerical relativity. I'm a bit confused. So is it that the perturbation is simple in a way that one can do some simulations easier?
No, it's not in that sense. So I emphasized here in this talk that perturbation theory is simpler. This is not directly relevant for numerical relativity because numerical relativity is non-linear. But it's not just that perturbation theory is easier here. As I said, this is really choice of variables. This is powerful choice of variables. The metric is encoded here in some clever way. It's possible that this can be useful for numerical relativity. So on this, I could add a few more statements. So you probably heard about Ashtekar Hamiltonian formalism for GR. So this Ashtekar Hamiltonian formalism is or arises if you take 3+1 decomposition of Plebanski action. So what Ashtekar discovered in like 86, 87 turned out later that it could have been discovered by Plebanski himself if he took 3+1 decomposition of his action. Ashtekar formalism is, so the constraints are polynomial and all this stuff, but it's a formalism, it's a Hamiltonian formalism, it's a formalism in which you think about GR as evolving, initial data which evolve. This is exactly the context of numerical relativity. It is possible that this choice of variables here that I'm describing is useful. Of course, this idea has been tried by people, particularly in applications to numerical relativity. It turned out to be not directly useful, or at least people didn't figure out how it can be useful so far. And actually the problem turned out to be the complex character of these variables. So if you want to describe Lorentzian geometry, which one has to for numerical relativity, then these basic fields are complex, and this is not nice for anything one does with the computer, because with the computer you want to put on the grid, you want to evolve real variables. But it's possible that people haven't tried everything here. So this difficulty with complex nature is there, and this is what prevented any real progress to be made. But at the same time, if one just writes these equations, kind of ignoring the fact that they're complex, then there is a very beautiful story the equations become much more compact than in the usual formalism. So of course there is this Ashtekar story, it is very well known, but the new twist to this story, and this is what I've done with a PhD student of mine, we gauge fixed the arising evolution equations in some nice way, motivated by this Plebanski complex that I described. And the gauge fixed equations, which are the ones that you want to evolve, because before one evolves, one needs to do the gauge fixing, otherwise evolution equations are simply not defined or unstable. So the gauge fixed equations continue to take very simple, compact form. So it is in this sense that there could be some hope for usage of this in numerical relativity. But at the moment, the stumbling block is the complex nature of these equations. And I don't know what to do with that, but there is some beauty in the structure of equations.
So the gauge fixed version that you mentioned is the work that you did this year, earlier this year.
Well, the gauge fixed version of evolution equations is not out yet.
Okay.
I have a PhD student who wrote his dissertation on it. He's defending it soon, but he has not put out this on the archive.
Okay, so this paper, Plebanski complex, is not...
Plebanski complex is out, yes.
Okay.
In fact, Plebanski complex is a paper written with the same PhD student.
Can I also ask a question?
Yes, of course.
Hi, Kirill, and thanks for the nice talk. I mean, my question is, how do you see the renormalizability of gravity in this formalism? I mean, how do you do power counting and so on in this formalism? I guess it's from resolving the constraints and so on, but still, I mean, that's question number one. And question number two, since you just mentioned the relation to the Ashtekar formalism, have you looked at possibly at two-dimensional reductions of these models? Because when you reduce on spacetimes with two Killing vectors, right, you get some integrable sigma mod principle, and I believe this should be related to this approach, first-order approach to sigma models. That's what I call like Grosvenor models and so on, somehow, which also seems much nicer than the traditional formulation. So I'm just wondering if you...
Okay, for the second question, the answer is no, I haven't looked at this. This is probably very interesting. I would like to look at it more. So maybe it's sometimes in the future. I agree. This is a very natural question to ask. But I haven't
just let me comment on that, because there was like old paper of, I think, Brodbeck and Sagerman, who studied Ashtekar variables, dimensional reductions, I think, of Ashtekar variables to two dimensions, and they found that the, say, Lux pairs of sigma models that they get are what is known as ultra-local, so which is much nicer than the typical non-ultra-local Lux pairs that people get in traditional formulations of sigma models. And also in this...
I don't know much about this, but I agree, this is a very natural question.
Okay.
For the first question, renormalizability, that's easier. Indeed, there is simple power counting. So this connection has dimension 1, the sigma field, the natural mass dimension for it, I think, is 2. So it's, or at least the perturbed sigma field, it's natural to give it mass dimension 2, so that the kinetic term is kind of sigma dA, and then it has mass dimension 4. And then one sees that the psi field has mass dimension 0, and in particular, any power of psi, this Lagrange multiplier field, which was imposing algebraic equation, any power of psi can start appearing in the renormalization. The Lagrange multiplier field, if I go back to my Plebanski action.
Yeah, I mean, how do you deal with the Lagrange multiplier field? Like, it doesn't have a propagator, right? Or
it does not have a propagator, no.
So how do you construct perturbation theory?
How do you construct perturbation theory here? Well, one way is to solve these constraints. And so solving these constraints constructs sigma from a frame. Then, so sigma that satisfies the constraint is basically frame self-dual part of. This is one way. You solve the constraint, then the action is just self-dual part of frame times f, and this has a nice expansion. However, this is not often the best way of dealing with perturbation theory. There are some other tricks that can be done. I don't want to describe too many of them, but At the same time, so this is the point I started making. I said that at the level of this action, before you solve the constraints, I wanted to say that psi has natural mass dimension 0, and then powers of psi can be produced as a result of, well, in particular, some Cantor terms can be powers of psi. This corresponds to one's intuition, because psi here on shell, this Lagrange multiplier field becomes Weyl curvature, the self-dual part of Weyl curvature. So powers of psi are standard powers of Riemann curvature. Well, another simple comment is that, of course, this is non-renormalizable. So, for example, if you solve for, if you know the sigma comes from the frame, this eliminates the second term. And then you expand the first term, you see that there is interaction with negative mass dimension coupling constant in front of it, because that it takes the form of there is a term HH. So if I denote my metric perturbation by H, then from sigma comes term, because sigma is quadratic in metric perturbation. There is HHDA term. So, for example, already that term it will have negative mass dimension coupling constant. So it's only normalizable exactly as in the usual formalism. But there are several versions of perturbation theory that one can do. So there are some. So one thing you can do, for example, with this Plebanski action is to integrate out sigma, because sigma in this action appears algebraically. You integrate it out. You get an action which depends only on f and Lagrange multipliers. If one wants, one can also integrate out Lagrange multipliers and get an action that depends just on f, but that's not as useful. But there is a nice simple action that depends on Lagrange multipliers and f that also has perturbative expansion, and that perturbative expansion is useful as well. Starting from here, there are several versions of perturbation theory that can be useful in different situations.
Okay, thank you.
I'm not sure I answered your question completely, but the easy answer is that, yeah, this formalism is as non-renormalizable as any other, but details of how this manifests itself, I don't think they're completely understood. For example, even Einstein-Cartan details, how do you understand non-renormalizability in that case? This is not really. There is some intuition for how it should go. We expect that the story just repeats the usual metric story, but details have not been worked out, at least as far as I know. The metric case, of course, is very well studied, right? But even Einstein-Cartan, with the connection and the need for the propagator for the connection, I don't think I've seen details of that story anywhere in the literature.
There was a slight jump. So while describing the Einstein-Cartan, you then started to describe the two-form formulation, but there was no clear connection, right? How to start from one and go to the other.
Yes, that I didn't explain. The clear connection is that, so the sigma in terms of the frame formalism is obtained. It's just the frame self-dual part of. That's the meaning of the sigmas.
Yeah, it's kind of quadratic in the Cartan field.
It's quadratic in the frame, yes. And if one takes this point of view, this eliminates this term, because this constraint, algebraic constraint on sigma, is then solved. One obtains an action which can be called chiral Einstein-Cartan, which is just the Einstein-Cartan, this action with a self-dual projector inserted here. So that's the link between the two. But of course, the point of view of Plebanski formalism is that the frame is not the fundamental field. The two forms are fundamental. So the whole what I described is really setting up the formalism in which two forms are fundamental rather than the frame. If you take a point of view that frame is fundamental, then it's not so surprising that a formalism like this exists, but it also just becomes a version of the usual frame formalism. What is beautiful and striking is that one can take a viewpoint that two forms encode everything. They are the basic dynamical objects.
Yeah, in a sense, that for the statement would be that for everything one can compute, every observable or whatever, we will only see frames appearing in pairs somehow. Only like the dependence should come in terms of these two forms, and then that would make them just redundant description of the two forms.
Yes. Of course, this is only true in vacuum. If you start thinking about coupling to matter, this becomes more tricky. For example, with fermions, this is clearly not the case. Fermions like the frame field. And so, of course, there are some subtleties and difficulties in coupling theory like these two fermions. But in vacuum, this is possible and powerful choice of variables. It's like, so the basic intuition that I would like to sell to you is that Einstein GR, metric GR is complicated, nonlinear. This is also nonlinear, but kind of less nonlinear. These variables linearize. They're better suited for the description of geometry.
If you think in terms of linearization, so Pierce-Pauli is actually quite nice, right? Is there any advantage compared to Pierce-Pauli in terms of like linearization theory?
So think about Pierce-Pauli. Pierce-Pauli, it's not true that the second order operator that appears in terms of, that second order operator that appears in linearization of GR, that second order operator is not a square of some nice first order operator. It's just the box. Of course, one can say that square root of box is the Dirac, but which Dirac operator is relevant in the case of GR? There is no Dirac operator that is relevant. So here the statement is that Einstein condition, or second order operator of Einstein theory, in terms of these variables, there is a natural square root. So
the main advantage is that it's first order. And
it's first order, yes. It takes, this formalism takes a square root of Einstein equations, of linearized Einstein equations. This is what this Plebanski complex does. There is a nice first order elliptic operator that can be written down, and Einstein condition is basically this elliptic operator times the adjoint.
I think you mentioned, but just to remind myself, so you can integrate out the sigmas here, right? The Plebanski action, but that makes more sense when you have cosmological constant.
Well, in flat space it's also possible, but it is less useful because so the action one gets is kind of 1 over this matrix FF. If lambda is not there, then you get 1 over psi FF, but psi wants to be almost 0 in flat space because psi is curvature, and so that gives you not very useful perturbation theory. You get 1 over 0. But if lambda is different from 0, then this is very useful perturbation theory.
And is there, you mentioned that the Lorentzian signature can be also described. Is there like natural extension of this action for the Lorentzian?
It's the same action. It's just you put factor of I in front, imaginary unit. And then the action is not manifestly real, but one can show that it becomes real on shell. So if sigma satisfies reality conditions and you go on shell for all the fields apart from sigma, then the action becomes real.
Normally we require reality of the action off shell, right?
Well, here it would not be real off shell. Why do we require reality of the action off shell?
I guess for the path integral to be well defined.
But how? I mean, the usual Lorentzian path integral, Lorentzian time is I in front of the action. And anyway, we define it in a tricky way. In quantum field theory, there is analytic conjugation involved in the definition of path integral. The usual statement is that action should be real for unitarity. But unitarity is for physical processes. Unitarity only requires that on-shell action is real, which is true here. So I'm not sure I see why off-shell action should be real.
Potentially there could be classical unitarity that might require only on-shell action to be real, but then quantum perturbations might be breaking this unitarity if your off-shell action is not real.
No, because of the on-shell formalism, right? We now understand that one just takes basically scattering tree-level processes and fuse them together using generalized unitarity. So it's all dictated by what happens at the tree level. Even quantum effects, they can be obtained by unitarity. So yeah, if tree-level unitarity is there, then it's unitary. Of course, there could be some subtleties which I'm missing, but I don't see
I also never thought about this.
what they are.
So in this formulation, is there a computation that is done or can be done that is not possible in other formulations?
So far, there is no such calculation. So far, everything that I've done or other people have done in this formalism is it has an analog in the usual formalism.
However, the derivation might be simpler.
Yeah, in many cases, there is a lot of simplicity. Like facts which are very difficult to establish in the usual formalism here come with little work.
So you mentioned Ashtekar. I mean, I don't remember exactly the Hamiltonian formulation, but I imagine that there the variables are not two forms, but if we decompose these two forms into 3+1, then they also become kind of vectors.
Yeah, they start their life as two forms on the spatial slice, exactly this kind of R3 valued two forms on the spatial slice. But then one dualizes, and one talks about densitized vector fields, which are also R3 valued. These are the E in Ashtekar formulas. In Ashtekar Hamiltonian, it's kind of E and F. So E is precisely you take the projection of sigma to the spatial slice, and then you dualize on the spatial slice.
And the relation to ADM is obvious? Or
no? Yes and no. So this E on the spatial slice is just the triad for the spatial metric. That's obvious. But the way connection is encoded is more interesting. So it turns out that this A, well, on shell, this A is the self-dual part of the spin connection. But then when one works out what that is in ADM is, so A becomes, or the spatial projection of A is gamma plus I times extrinsic curvature. So the gamma plus IK. So connection is necessarily complex, or at least it's complex when kind of the time derivative of the metric is different from zero. Connection is necessarily complex. And in particular, Lorentzian version of evolution equations that will have factors of I everywhere, which is not very surprising. It's like if you want to take Dirac operator, if you want to take a square root of your box in Lorentzian signature and write Dirac operator, there will be factors of I in that Dirac operator. So that's the explanation why the factors of I appear. Because this formalism takes the square root of Einstein equations.
Somewhat unrelated, or I mean, at least I don't know exactly the relation. So question that is, there is some work that claims to relate this Plebanski formulation of gravity to weak force. Can you comment
Yes,
on
I've
that?
seen works like this, yes, indeed.
I mean, if you know what they exactly try to claim, can you comment?
Well, I think the basic idea is that so here in Plebanski formalism, one uses single SU2 to describe gravity, because this is a chiral formalism. Only chiral half of Lorentz group participates. And I think the idea of all these works is that, well, let's take the other SU2 to describe the weak force. Precisely the details of how this is realized, I cannot comment on, but that's the basic idea. So again, full Lorentz or full, in Euclidean signature, full orthogonal group is two copies of SU2. And then they say, well, let's use one for describing gravity, the other one for describing the weak force. But I don't know whether this is viable.